Good morning all. The 8-bit computer needs another outing, so I've dug it out and I'm just replacing wires at the moment because I want to sort of vaguely color code it. This section here, which provides go-to addresses, is going to be sort of vaguely red. I'm kind of using yellows, browns, oranges type colors. This section over here is going to be vaguely blue. This provides the actual instructions, which are the copy to and from addresses, because this computer only has one instruction, which is copy to a register and from one register to another register. So I've got to make decisions where this is all going, and one thing I've decided already is that it's all going to go CMOS. So I'm going to lose this LSTTL and go for 74HC series chips because they are more freely available, and possibly some of them will have to be surface mount because 74HC is increasingly available in surface mount, not dip package like this. That one goes there. I think these 5 wires all are the same length, so that's fine. Now, of course, surface mount won't plug into a breadboard, but they will if you put them on these little dip boards. So I'm going to buy some more of these 16-pin dip boards. I think that's 600 across there. I think we worked out. Oh no, it might be 500. Actually, yes, I think it is 500 because it sits. Let's get a chip. It sits 1/10 either side of the chip's leg spacings. These are 300. Mils they are, or 300 thou, so that's 500. So I'm going to get some 16-pin and some 20-pin ones because that seems to be mostly the chips I'm using. Right, so I've removed all these blue wires and replaced them with something a little bit more color coordinated and vaguely red. I've used orange and yellow. I didn't want to actually use red because red I'm only going to use for VCC. White I've used there for the clock going into the latch there. This is actually blue, but I'll have to replace that at some point with something a bit more color coordinated, but I'm going to have to put that back just for the moment so I can see the data that's coming out of this RAM chip. So let's put some power onto this thing. I've just literally pulled wires out and put them back in, so I may have made a mistake. Let's plug that in like that and like that. Actually, no, that's not going to work because I'm not really using this top set of breadboards, so that's going to have to go down here, plug it in there, and plug it in there, and I'll get in and see if it works. Let's switch on. Clock not running. Clock is running. Yeah, that's doing something. Let's turn off that light. So I'm just using daylight now. Oh yeah, daylight's pretty grim today. There isn't a lot of daylight. Yeah, that's doing something. What I want to do now is program let's reset it to 0. So it is following a sequence. Let's put it into single step and just program a few instructions to make sure it's doing what it's meant to. So that puts it to address 0, in which I will write, oh yeah, I've changed this switch and this one's not loosened up yet. I'll write a 1. When I clock that, the 1 goes into there, because the data coming out of the RAM, which is on orange, goes to the switch so that I can write to it. Write is this brown wire here, which goes to the right pin. The orange data also goes into the input of this latch, and the outputs of this latch come back on yellow to the 8 address lines. So in address 1, I want data 2. So I'm going to do it like that. That's like that. Move on. The 2 moves into there because, of course, it's latched through the latch. And then I want 3, and so on. Move on. So perhaps I'll go to 4. That's 1, 0, 0. And then possibly at location 4, I'll head back to 0. And if you free run that, then it just does a count from 0 up to 4. So it's doing 5 counts. Well, that seems to work. So then the next thing I need to do is bring these 8 yellow lines, which are the address lines of the RAM chip, copy them onto the first 8 pins of this RAM, because these two RAMs are going to have the same address fed into them. Then the data for this RAM will go to this switch bank, and there'll be another write switch, or possibly I can have a common write switch that I can write to both RAMs simultaneously. They're going to act as one RAM 16 bits wide. Then the data lines are also going to go out to these two address decoders, which are HC138. They're going to replace these LS138. It makes sense for them to be on this side because they're driven by this CMOS RAM chip over to here. And then these will have the individual select lines which go off to the various latch and buffer chips, which will be along here. Now all these LS374s, which have data and input and output sort of higgledy-piggledy on both sides of the chip, will be replaced with these HC574s, which have all the inputs on one side and all the outputs on the other. So the busing along here will look much, much neater, much more like this yellow wire down here. Now, I've been thinking about the arithmetic logic unit because, of course, this computer is going to need an arithmetic logic unit. So I'm thinking of going for something like this, an adder, which I think you can draw kind of like that, adder. Now that will have a carry in, so that you can, it'll also have a carry pass through from sort of 4 bits of it to the other 4 bits. And then I'm thinking of having two logical units, logic unit A and B, like this. So those will feed the adder, but each logical unit will have 2 inputs, so an A input and a B input, and an A input for that one and a B input. That means we can apply logical transformations to A and B, and they get passed through the adder. Now there's no access to the output of the logical units because it doesn't really matter. If you just want to say add A and B, you just put A through there, B through there, and it adds A and B. If you just want access to A, you can add A and 0. You can make this logical unit turn B into just 0, and that will just give you A. If you want 2A, A multiplied by 2, then you simply route A through this logical unit and also A through this logical unit. So you route that one through there. That'll give you A added to A, so you'll get 2A on the output, and that's the equivalent of multiplying by 2, which is a left shift. Now if you want to subtract, so say A minus B, you put A on one side of the adder and you put the 2's complement of B on the other side, so that you effectively subtract B from A. Now the 2's complement of B is the inverse of B, and the logical unit will be able to do an invert. Plus 1, you invert and add 1. Now plus 1 is relatively straightforward. You just put a 1 on the carry in. The adder has this ability to have a plus 1. That enables you to do subtract. You can do A subtract B by inverting B and adding 1. You can also do B by passing that through. Subtract A by inverting A and adding 1. And also with the add 1 ability on the adder can work as an increment. So say you want to increment A, you can put A straight through that logical unit into the adder. B would be, this one would be set to 0, so you add nothing to A, so you've got A plus 0, and then you set this high, so you've got A plus 1, that's the increment of A. You can also decrement by, I think you can decrement by just inverting. If you invert with the logical unit one of these inputs, the output is A minus 1. I believe that's true. Now the only thing I know that this can't do is it can't do a right shift, because a right shift is a divide by 2, and there's no configuration of this that can do a divide by 2. So I'll probably have a right shift register. Now these were my two 1-bit shift registers. I think one is a shift left and one is a shift right. Don't need the shift left because that is a multiply by 2, which we can do by simply adding A to itself or adding B to itself through the adder. So I can get rid of one of these, keep the right shift, and then right shift will go through a special purpose register. Most other arithmetic and logic calculations will go through the ALU. If you get an overflow from here, of course you've got to carry out. Now that can go off to some register somewhere and to be able to be read, because this might enable sort of conditional branching. If we can read this carry out and transfer it to a conditional branching register, then we could do sort of conditional branching on the condition of a carry. It may also be possible to get a 0 result out of this somehow. Probably need an additional gate, something like an 8-input OR gate, which can give you a 0 result, so that we have a couple of basic flags. So how am I going to build this in hardware? Well, the adder can be 2 times HC283. The HC283 is a 4-bit adder, so 2 of those will give me an 8-bit adder. These are 8-bit buses, /8. They're 8-bit buses. These are all 8-bit buses. How do I build the logical units? Well, they're pretty miraculous, really. They are going to be little stacks, and I mean vertical stacks, quite possibly, of, now what was it, HC253, I think it is, which is actually, so it'll be 4 here, 4 times, and also 4 times HC253 there. They're actually multiplexers. So if you have a multiplexer, a 4-to-1, so you've got 4 lines going in, 1 line coming out, and you've got 2 select lines here, and by putting a binary code on there, you decide which of these 4 data inputs go to the data output. What's interesting is that if you treat these select lines here as A and B, or possibly the other way around, you can actually use a 4-input 1-output multiplexer or data selector as a configurable logic gate. So let's draw the truth table for example, an OR gate. Now, how am I going to do this? Right, yeah, so these are A and B. Now, it doesn't really matter which way round they are, but the 4 combinations are 0, 0, 0, 1, 1, 0, and 1, 1. If I draw the truth table for OR, which is, it'll be 0 there and 1, 1, 1. If any of the inputs is high, the outputs are high. That's an OR truth table. But if I want it to be an AND, then I simply do a different truth table, which is 0, 0, 0, 1. So the output is only high if both the inputs are high. Then that gives me an AND gate. Now, if you simply put this truth table on these 4 select lines and use them as the logic unit configuration lines, so if you want this multiplexer to be an OR gate, you simply put a 0, 1, 1, 1 on there and sort of latch it on and just hold it there. Now, whenever you get combinations of A and B here, you'll get an OR result out here. Change this configuration to the AND, the 0, 0, 0, 1, and any combination of A and B, you'll get the AND truth table coming out of here. And there are 16, of course, combinations here, and they're really interesting things. So, for example, what's the one for exclusive OR? It's a 1 when they're different, isn't it? So it's a 1 there and a 1 there and a 0 and a 0. That is an exclusive OR. If you put 0, 1, 1, 0 on these 4 lines, then putting your inputs A and B into here, you'll get the exclusive OR function out of the same 4-to-1 multiplexer. It's a logic unit. You can also create the inverse, like if you want an XNOR, I think it's called XNOR, which is simply XOR with an inverted output, then you'd simply put 1, 0, 0, 1, and that's an exclusive OR function, but the output is the inverse of the XOR function. And as I say, you've got 16 different combinations of these. Some of them are quite interesting. So, for example, if you put 0, 0, 0, 0 on these 4 lines, then irrespective of what the A and B patterns are, you'll get a 0 out. So this isn't really a gate, it's just provide a 0 out for every combination of inputs. This is simply a 0, 0 gate. Now, one of the other ones that I needed from the logical unit was something like an A pass-through. If I just want to pass A through there, and say I also want to pass A through here, I just want simply the output to be whatever A is. Well, A here is 0011. So if I make another configuration of 0011, then the Q output, if that's Q, will simply be A, and B is ignored. So this is just a sort of A function. It just lets A pass straight through. Now, if you want to do this on 8-bit words, you need 8 of these 4-to-1 multiplexers. Now, you can get a chip, and it's the HC253, which has 2 of them. So what you would need to do is have 2 outputs, and you'd have all the inputs. So this might be A7 and B7, A6 and B6, all the way down to A0. So you'd have 8 of these if you want 8-bit wide logic units, and that would be 4 of these HC253 chips. And it did occur to me, because you've got to parallel all these inputs up across all 8 units, that actually you could have these little chips, they're 16-pin chips, stacked vertically on these little boards using surface mount. Probably not that one would be better, using sort of long pin stackable headers, and you'd simply stack these up to bus these chips in a vertical arrangement. Now, if you're going to bus these, all of these latch chips here will be bussed. Why not bus them vertically as well on 20-pin little surface mount breakout boards like this? Part of this computer could be built vertically. Now, I do have one kind of paradoxical situation at the moment, and that is that this computer has no literals. There is only one instruction in here, and it is simply copy from one of these latches to another, and you just do sequences of copying one latch to another, whichever the read and write latches might be. Now, to set up these logical units, we need to put patterns of digits to set up what gate type you're using onto these multiplexer input lines, these data lines, but they become the configurator lines if you're using it as a logic unit. But because I don't have literals, I can't create these patterns to put them on here. And I did think of having sort of one literal, perhaps 0, somewhere on a pre-wired register, and then using the logical unit to create other literals from that. But because I can't configure the logical unit, because I have no literals, I can't use it to create the literals. It's kind of a chicken and egg situation. So I've got to think of another way of creating literals. And I did think of something, and this was just last night, and it's very vague in my head at the moment, but I did think if you write to, you've got 4 bits coming from the RAM as your read latch and 4 bits as your write latch. I did think a couple of the write latches could actually have a synthetic read, which wouldn't read from a latch on the main data bus. It would actually read the read address pattern. And if you did that twice, you could build up a literal in 2 nibbles. It's early stages, but that's probably how I'll have to do it. And the final thing, of course, is conditional branching. For this thing to be Turing complete, it needs conditional branching. And at the moment, my idea is simply to read this carry flag. So you might do a branch on carry, copy that to another register, which is hardwired to one of the high order address lines of the RAM chip, so that if the carry is high, the RAM chip simply jumps 256 locations to a different part of the RAM. You can think of it as sort of banked RAM, where that's bank 0, bank 1, bank 2, and so on. It will jump to another bank. Now, as long as I have the ability to write to that bank, so I'll need sort of bank select switches while I'm programming this thing, I can use either a carry flag or a 0 flag, copy it into this latch, which will directly change the hardware settings on these RAMs, and that will give you your conditional branching. But again, this is early thoughts for this computer. So that's kind of it for the 8-bit computer for the moment. It's a lot of thinking at the moment, because there's a lot more to go into this. This really is only at its early stages of development. I've got the ability to step through the program. I've got my clock and single stepper, and I've got my pseudo program counter, which is simply a latch taking go-tos. This is the chip holding all the go-tos and writing them back onto the address line, so that 3 goes to 4, 4 goes to 0, 0 goes to 1, and so on. Need to wire up the other RAM so that I've got my actual instructions, my read and write addresses, and start using that to select the various registers that are being read from and written to. Yes, but for the moment, those are my thoughts. Cheerio.